Hello everyone. Today we will study another probability distribution called Poisson distribution. First of all, let me introduce what it is. Consider a set that contains only two elements, success and failure. Consider a set that contains only two elements, success and failure. When we choose an element from the set, assume the chance of getting success is unknown. Assume the chance of getting success from the set is unknown. Now, when an element is chosen from the set n times, when an element is chosen from the set n times with replacement, let me choose an element from the set, write down what it is, and put it back, and choose it again. When an element is chosen from the set n times with replacement, we estimate that based on these n trials, we estimate that the probability of getting success from the set is P. So this P is the estimated probability, it's not actual probability. This is the estimated probability. Based on these n trials, we choose element from the set n times. We pick element from the set, write down what it is, put it back, choose it again. Write down what it is, put it back, and choose it again. Based on these n trials, we estimate that the probability of getting success from the set is P. So this P is not the actual probability, it's an estimated probability. This P is not an actual probability, it's an estimated probability of getting success. Now next, let lambda be defined as n times P. Let lambda be defined as n times P. Then P can be rewritten as lambda over n. Then P can be rewritten as lambda over n. Next, let the random variable x let the random variable x represent the actual number of chosen success. Let the random variable x represent the actual number of chosen success. Then we say this x has a Poisson distribution. Then we say x has a Poisson distribution. How do we find its probability function? How do we find its probability function? This x is very, very close to a binomial distribution. Since we know n, we know the estimated probability. This x is very, very close to a binomial distribution. The only difference, for binomial distribution, we know the actual probability. But here, we don't know the actual probability of getting success. So this is not binomial distribution, but it's very, very close to a binomial distribution. So this x is very, very close to a binomial distribution. So we can use binomial distribution to approximate a formula for a Poisson distribution. The formula for binomial distribution is here. This random value of x is very close to a binomial distribution. It's very close to a binomial distribution. So f of x is very close to, the probability function is very close to n choose x. That's the formula for binomial distribution. N choose x, p to the power x times 1 minus p to the power of n minus x. This is a formula for binomial distribution, but this x is not exactly the binomial distribution because we don't know the actual probability of getting success. We don't know the exact probability of getting success. This is an estimated probability based on this n trials. This is an estimated probability based on this n trials. So, in order to find the actual probability, we need to have infinitely many trials. This n must be approached to infinity. So in order to have an actual probability, we must take limit as n approaches to infinity. In order to find actual probabilities, we must take limit as n approaches to infinity. The probability based on infinitely many trials is the actual probability. So take limit as n approaches to infinity. That's the actual probability function for this random variable x. That's an actual probability function for this random variable x. Now, how do we take a limit here? Here, n choose x is n factorial m minus x factorial times x factorial. P is lambda over n. P is lambda over n. To the power of x. 1 minus p. P is lambda over n. To the power of m minus x. Next, I have limit n approaches to infinity. N factorial over m minus s factorial times s factorial. Here, lambda over n raised to the power x can be rewritten as lambda to the power x over n to the power x. The last part, 1 minus lambda over n to the power of m minus x, it can be rewritten as 1 minus lambda over n to the power of n times 1 minus lambda over n to the power of negative x. Last part can be written as this, power n power negative x. Next, we are taking limit as n approaches to infinity. So we treat lambda x and x as constant. We treat lambda x and x as constant. I can pull it outside. So I pull out lambda to the power x and x factorial outside. If I pull out lambda to the power x and x factorial, what's left here is n factorial on the top. On the bottom we have n minus x factorial times n to the power x times 1 minus lambda over n to the power n times 1 minus lambda over n raised to negative x. Next, we take a limit for each part individually. Take a limit for each one individually. Lambda to the power x over s factorial times limit n goes to infinity, n factorial, let me write n to the power x in the front, times m minus x factorial times the limit n goes to infinity, 1 minus lambda over n to the power of n times the limit n goes to infinity, 1 minus lambda over n raised to negative x. So take each limit individually. Let me take the first limit first. For the first limit, n goes to infinity. The numerator is n factorial. N factorial is n times m minus 1, m minus 2, m minus x plus 1, m minus x, m minus x minus 1, 3, 2, 1. This is the numerator, n factorial. The denominator, m minus x factorial, is m minus x, m minus x minus 1, 3, 2, 1. This is m minus x factorial. Now, how about n to the power of x? n to the power of x means they are x n's multiplied together. N to the power of x means they are n times n times n. They are x times x factors. They are x factors, x n's multiplied together. How many factors do we have here? From n to n minus x plus 1. How many factors do we have here? How many factors do we have here? From n minus 1, n minus 2, n minus x plus 1. How many factors do we have here? Let's try some simple numbers. From n to m minus x plus 1. How many terms do we have? Say from 10 to 7. How many terms do we have? From 10 to 7, how many terms do we have? 10, 9, 8, 7. There are 4 terms. To find out how many terms, we take 10 minus 7 plus 1. We can find out how many factors. Take 10 minus 7 plus 1. We can find out there are 4 factors. And similarly, from 20 to 14, how many factors? We can check. 20, 19, 18, 17, 16, 15, 14. 1, 2, 3, 4, 5, 6, 7. We can take 20, the first term, minus last term, plus 1. 20 minus 14 plus 1, that's 7. So, same argument, we can take this. Take the first term, minus last term, then plus 1. n minus x plus 1. First term minus last term plus 1. Then we can find out how many terms are there. This can be rewritten as n minus n plus x minus 1 plus 1. Cancel n, cancel 1. There are x. We have x. So there are x factors. There are also x factors. So we have top, we have n, we have x factors. On the bottom, n factor, n to the power x is also x factors. We have n times n times n times n. There are same amount of factors here. There are same amount of factors. Now here you can see that this can cancel, this can cancel, this can cancel. Everything after n minus x can cancel. What's left? What's left is the limit n goes to infinity, n over n times n minus 1 over n times n minus 2 over n n minus x plus 1 over n. As n goes to infinity, this limit is 1. As n goes to infinity, this limit is also 1. If we do L'Hopital's rule here, this is 1. When n goes to infinity, if we do L'Hopital's rule here, this is also 1. When n goes to infinity, this is also 1. So we get 1 times 1 times 1 times 1 times 1, which is 1. So the first limit is 1. The first limit is 1. How about the second limit? Second limit, limit n goes to infinity. 1 minus lambda over n to the power n. If we plug infinity for n, lambda over infinity is 0. n by itself is infinity. 1 raised to infinity, that's indeterminate form. 1 raised to infinity is not 1. This is indeterminate form. So how do we take limit here? Let y equal to 1 minus lambda over n to the power n. Apply natural log to both sides. Apply natural log to both sides. Then I can bring exponent to the front. Ln of y is n times ln of 1 minus lambda over n. Then the right side can be rewritten as ln of 1 minus lambda over n over n raised to negative 1. N raised to negative 1 can be rewritten as 1 over n. Now take limit as n approaches to infinity. Ln of 1 minus lambda over n over 1 over n. When n approaches to infinity, lambda over infinity is 0. 1 minus 0 is 1. And on the bottom, 1 over infinity is also 0. Ln of 1 is 0. 1 over infinity is also 0. That's in the form of, that's called indeterminate form. Here we can use L'Hopital's rule. Here we can use L'Hopital's rule. When we get 0 over 0, we can use L'Hopital's rule. So before I use L'Hopital's rule, let me rewrite the top and the bottom first. The top can be rewritten as net Ln of 1 minus lambda n raised to negative 1. The bottom is n raised to negative 1. If we use L'Hopital's rule here, the top is 1 over the inside times the derivative of the inside. It will be negative positive lambda times n raised to negative 2 over negative 1 times n raised to negative 2. Then I can multiply, then simplify first. I can multiply top and bottom by n squared. I can multiply top and bottom by n squared. Then n squared times n raised to negative 2 will be 1. They get cancelled. What's left here is 1 over 1 minus lambda over n times lambda over negative 1. Then when n goes to infinity, lambda over infinity is 0. We have 1 over 1 minus 0 times lambda over negative 1. So the numerator is lambda, denominator is negative 1. Lambda over negative 1 is negative lambda. That means as n goes to infinity, Ln of y is negative lambda. So Ln of y is negative lambda. That means y is e raised to negative lambda. Y is e raised to negative lambda. So this limit here is e raised to negative lambda. That's the second limit. That's the second limit. E raised to negative lambda. Now how about the third limit? For the third limit, as n goes to infinity, 1 minus lambda over n raised to negative x. As n goes to infinity, we have 1 minus 0 raised to the power of negative x. 1 minus 0 is 1, and we know 1 raised to any power is 1. So as n goes to infinity, this limit is 1. So together, we have lambda to the power x over x factorial times 1 times 1 times e raised to negative lambda. So the probability function f of x is e raised to negative lambda, lambda to the power of x over s factorial. That's the probability function. That's the probability function for Poisson distribution. And here, x, what could x be? X represents the actual number of chosen success. X represents the actual number of chosen success. Since n goes to infinity, the actual number of chosen success could be 0, 1, 2 up to infinity. x represents the actual number of chosen success. As n goes to infinity, s could be 0, 1, 2, 3, 4, 5 up to infinity. And support of x is the set of all non-negative integers, 0, 1, 2, and so on. The notation for Poisson distribution is x equal to Poisson in this formula. The only parameter here is lambda. E is a constant, x is the variable. The only parameter is lambda. So this is the Poisson distribution. That's the probability function, that's the support, that's the notation. Note, in general, under a fixed condition, lambda represents the average number of occurrence of an event. And x represents the actual number of occurrence of an event. X is the actual number of an occurrence of an event. For example here, lambda equal to n times p, the total number of trial times probability, that's the expected number of occurrence of an event. And x is the actual number of the occurrence of the event. This is Poisson distribution. Next, let's look at an example here. Let the random variable x have a Poisson distribution with lambda equal to 5. Find each of the following probabilities. Part A, probability that s equal to 4. Part B, probability that s equal to 7. Part C, probability of s is less than 4. Part D, probability of x is greater than or equal to 2. So this number 5 here represents lambda. So to find the following probabilities. So let's set up a problem first. First of all, let's write down the probability function. F of x is always lambda to the power of x, e raised to the power of negative lambda, over s factorial. Support of x is the set of all non-negative integers, 0, 1, 2, 3, up to infinity. For the probability function, we need to plug in lambda. It's a function of x. We need to plug in lambda. For the probability function, we need to plug in lambda. It's a function of x. This is a function of x. Plug in lambda. We have 5 to the power of x e raised to the power of negative 5 over s factorial. This is the probability function. And this is a support. Now, based on the probability function and the support, let's find each of the following probabilities. First probability. What's the probability that s equal to 4? Probability s equal to 4, that's f of 4. We plug in 4 for each x. We have 5 to the power of 4 e raised to negative 5 over 4 factorial. Then use calculator for the answer. Part B. What's the probability that s equal to 7? Probability that s equal to 7, that's f of 7. For f of 7, we plug in 7 for x. Plug in 7 for x. This number represents x. Plug in 7 for x. We get 5 to the power of 7 times e to the power of negative 5 over 7 factorial. Then use calculator for the answer. Part C. What's the probability that x is less than 4? Here, support is from 0 to infinity. So x less than 4 could be 0, 1, 2, and 3. That's f of 0 plus f of 1 plus f of 2 plus f of 3. Then plugging 0, 1, 2, 3 into the formula. F of 0, plugging 0 for x, we get 5 to the power 0 e raised to negative 5 over 0 factorial. F of 1, plugging 1 for x, we have 5 to the power 1 times e to the power of negative 5 over 1 factorial. F of 2, I plug in 2 for x. 5 to the power of 2 times e to the power of negative 5 over 2 factorial. For f of 3, we plug in 3 for x. I get 5 to the power of 3 e raised to negative 5 over 3 factorial. Then use calculator, compute each term, then add them up. Part D. What's the probability that x is greater than or equal to 2? If x is greater or equal to 2, we need to compute 2, 3, 4, 5. Support is from 2 to infinity. Support is from 0 to infinity. If x is greater or equal to 4, if x is greater than or equal to 2, we must compute x from 2, 3, 4, 5 up to infinity. It may be too many terms. It may be too many terms. So for probability that x is greater than or equal to 2, we can try to compute its complement. Then use 1 minus its complement. The complement of x greater or equal to 2 is the probability that x is less than 2. That's the opposite of x greater or equal to 2. That is x less than 2. Then probability that x less than 2, the support is from 0 to infinity. X less than 2 is 0 and 1. So 1 minus f of 0 plus f of 1. F of 0, for f of 0, plug in 0 for x. 5 to the power of 0 e to the power of negative 5 over 0 factorial. For f of 1, plug in 1 for x. 5 to the power of 1 times e to the power of negative 5 over 1 factorial. Then use calculator for the rest. Next example, a salesperson can sell an average of 6 TVs each day. Assume the number of sold TV has a Poisson distribution. In a given day, what's the probability that he sells 5 TV? Part B, in a given day, what's the probability that he sells nothing? Part C, in a given day, what's the probability that he sells at least 2 TVs? So this problem is about Poisson distribution. Let's set out the problem first. So let the random variable x represent the number of sold TV. in a given day. Let X represent the number of sold TV in a given day. Then we know X has a Poisson distribution. We know on average he can sell 6 TVs, so lambda is 6. If we know the average number of occurrence of an event, we can use Poisson distribution. Here lambda is 6. We know on average he can sell 6 TV in a day. Next, write down the formula. Formula for Poisson distribution is lambda to the power of X times e raised to negative lambda over X factorial. And if we plug in lambda, we have 6 to the power of X times e to the power of negative 6 over X factorial. This is a probability function. And next, write down the support. For Poisson distribution, the support is from 0 to infinity. Integers from 0 to infinity. Then, answer the question based on this. Answer the question. Part A. In a given day, what's the probability that he sells 5 TVs? So in part A, what we are looking for is probability that X equal to 5. What's the probability that he sells 5 TVs? Part A is probability that X equal to 5. So that's f of 5. We plug in 5 into the probability function. We have 6 to the power of 5 times e raised to negative 6 over 5 factorial. Then use calculator for the rest. Part B. In a given day, what's the probability that he sells nothing? Sells nothing means the number of sold TV is 0. Probability that S equal to 0. That's f of 0. For f of 0, plug in 0 for x. We have 6 to the power of 0, e to the power of negative 6 over 0 factorial. Then use calculator for the rest. This one is easier. 6 to the power of 0 is 1. 0 factorial is 1. That's e raised to negative 6. This one is easier. Part C. In a given day, what's the probability that he sells at least 2 TVs? In a given day, what's the probability that he sells at least 2 TVs? At least 2 means probability that X is greater than or equal to 2. If we compute probability that X is greater or equal to 2, we must compute f of 2, 3, 4, 5 up to infinity. There are too many terms. So easier way is we can compute the complement. The complement of X greater or equal to 2 is probability that X less than 2. The complement of probability that X is greater than or equal to 2 is probability that X is less than 2. If S is less than 2, then S could be 0, 1. Then we compute f of 0 and f of 1. For f of 0, we plug in 0 for X. We have 6 to the power of 0 times e raised to the power of negative 6 over 0 factorial. If I plug in 1, I have 6 raised to the power 1 e raised to negative 6 over 1 factorial. Then use calculator for the rest. Next example, vehicles visit a gas station at an average rate of 30 vehicles per hour. Assume the number of visiting vehicle has a Poisson distribution. Part A. What's the probability that no vehicles visit in a given minute? So this is Poisson distribution. Let's set down a problem first. Let the random variable x represent the number of visiting vehicles. in a given minute. For Poisson distribution, we must find lambda first. How do we find lambda? We know that vehicles visit an average rate of 30 vehicles per hour. Then how many vehicles will visit in a minute on average? How many vehicles will visit a gas station on average in a minute? So let's think of this. There are 30 vehicles visit in every 60 minutes. We try to find out how many vehicles will visit the gas station in 1 minute. Vehicle visit a gas station on average rate of 30 vehicles per hour. An hour means 60 minutes. We are looking for how many vehicles will visit a gas station in a minute. So we can solve this equation for lambda. If I cross multiply, I have 60 lambda equal to 30. So solve the equation for lambda equal to half. So on average, we expect half vehicle visit the gas station per minute, every minute. Every minute, on average, we expect a half vehicle will visit the gas station. That's lambda. So here, since I know lambda, I can say x is the Poisson distribution with lambda equal to half. Once I know lambda, I can run the formula. Probability function for Poisson distribution is lambda to the power of x, e raised to the power of negative lambda over s factorial. Then plug in lambda. Lambda is half e raised to negative lambda over x factorial. Now, this problem is asking what's the probability that no vehicle visit in a given minute. That's probability that s equal to 0. And also, I forget one thing, the support. Support is the set from 0, 1, 2 to infinity. Part A is asking what's the probability that no vehicles visit in a given minute. That means what's the probability that number of visiting vehicle equal to 0? What's the probability that the number of visiting vehicle equal to 0? Then plugging 0 into the formula, into the probability function. We have half to the power of 0, e raised to negative half over 0 factorial. 0 factorial is 1. Half to the power of 0 is 1. And so it's e raised to negative half. That's the probability that no vehicle visit in a given minute. That's the probability that no vehicles visit in a given minute. Part B. What's the probability that exactly 2 vehicles within a gas station in a given 3 minutes. What's the probability that exactly 2 vehicles visit a gas station in a given 3 minutes? We know that vehicle visit the gas station on an average rate of 30 vehicles per hour. Then on average, how many vehicles will visit in 3 minutes? We know that on average, 30 vehicles visit in 60 minutes. Then how many vehicles will visit in 3 minutes? So let's set down the problem first. Let x represent the number of visiting vehicles in a given 3 minutes. We know that on average, 30 vehicles will visit a gas station every hour. Then how many vehicles will visit in 3 minutes? So we know that 30 vehicles will visit in 360 minutes. Then lambda represents the average number of occurrence of an event. Assume a visiting vehicle represents the occurrence of an event. We're looking for the number of visiting vehicles in 3 minutes. What's given is that on average, 30 vehicles visit in 60 minutes. We try to find out on average how many vehicles visit in 3 minutes. That's our lambda. Lambda is average number of occurrence of an event. Then if I cross multiply, I have 60 lambda equal to 90. Solve an equation for lambda. Lambda equal to 3 over 2. Then what? X is the probability. X is the Poisson distribution. X has a Poisson distribution with lambda equal to 3 over 2. Run the probability function first. Probability function is lambda to the power of x e raised to negative lambda over x factorial. That's the probability function for Poisson distribution. Plug in lambda. Lambda is 3 over 2 e raised to 3 over 2 over s factorial. This is a probability function. And support, here support is 0, 1, 2 up to infinity. That's the support of x. Then based on this, let's answer the question. What's the probability that exactly 2 vehicles visit the gas station in a given 3 minutes? So what we are looking for is probability that s equal to 2, because x represents the number of visiting vehicles in a given 3 minutes. So we're looking for probability that the number of visiting vehicle equal to 2. Then plugging 2 into the probability function. Plugging 2 into the probability function here. Plugging 2 for x. Probability that s equal to 2 is f of 2. We're plugging 2 into the probability function. I have 3 over 2 to the power of x e raised to negative 3 over 2 over x factorial. Here x is 2. We're plugging 2 for every x. Then use calculator for the rest. Use calculator for the rest. Part C. What's the probability that at least 2 vehicles visit a gas station in a given 5 minutes? Let's set down the problem first. Let the random variable x represent the number of visiting vehicles in a given 5 minutes. The x represents the number of visiting vehicles in a given 5 minutes. And we know that here, x has a Poisson distribution. For Poisson distribution, we should find lambda first. Lambda is the average number of occurrence of an event. We try to find out on average. How many vehicles will visit a gas station in 5 minutes. We try to find out on average how many vehicles will visit a gas station in 5 minutes. According to the problem, we know that on average 30 vehicle widget per hour. So on average, 30 vehicles widget per hour. We try to find out how many vehicles will widget in a given 5 minutes. Then I can cross multiply. 60 lambda equal to 150. Then divide both sides by 60. Lambda equal to 5 over 2. That means on average, 2.5 vehicles will visit a gas station in 5 minutes. On average, 2.5 vehicles will visit a gas station in 5 minutes. So here x is a Poisson distribution. Lambda equal to 5 over 2. Next, let's write down the probability function. The formula is lambda to the power of x, e raised to negative lambda over x factorial. Plug in lambda first. Lambda is 5 over 2 raised to the power of x, e raised to negative 5 over 2. Over x factorial. Support of x. For Poisson distribution, support of x is always from 0 to infinity, integers from 0 to infinity. That's support of x. Then answer the question. What's the probability that at least 2 vehicles visit a gas station in a given 5 minutes? We're looking for probability that x is greater than or equal to 2. If x is greater than or equal to 2, based on the support, we need to compute x equal to 2, 3, 4, 5 up to infinity. It may be too many terms. A simple way is we can compute its complement. So the complement of x greater than or equal to 2 is probability that x less than 2. Probability that x less than 2 is f of 0 and f of 1. Probability that x less than 2 is f of 0 and f of 1. Add them up. Then subtract. F of 0, we plug in 0 for x. Plug in 0 for x. We have 5 over 2 to the power of 0. E raised to negative 5 over 2 over 0 factorial. For f of 1, plug in 1 for x. That's 5 over 2 to the power of 1 times e raised to negative 5 over 2 over 1 factorial. Then use calculator for the rest. Next example. In a factory, the probability of producing a defective toy is 0.002. In a box of 3,000 toys, what's the probability that exactly 4 toys are defective? What's the probability that exactly 4 toys are defective? First of all, we need to decide what kind of probability distribution it is. The x represents the number of defective toys. The x represents the number of defective toys in the box. First step, we need to decide what kind of distribution it is. Here, the probability for each toy to be defective is 0.002, and in the box there are 3,000 toys. We can consider this is n, this is p. This is probability being defective, and we have 3,000 toys, which means we have 3,000 trials. Consider each toy is a trial. We have 3,000 trials. That's n, that's p. So it looks like this binomial distribution. Assuming being defective means success. So the probability of being success is 0.002. And consider 3,000 toys represent 3,000 trials. So x is a binomial distribution. This x has a binomial distribution. For binomial distribution, there are two parameters, n and p. Here n is 3,000, p is 0.002, 0.002. Now, let's write down the probability function. For binomial distribution, the probability function is n choose x times p to the power of x times 1 minus p to the power of m minus x. Then if we plug in numbers, n is 3,000. P is 0.002. One minus p is 0.998 to the power of m minus x. N is 3,000 minus x. That's the probability function. And support of x. For binomial distribution, support of x is from 0, 1, 2 up to n. Here n is 3,000. That's the setup. Next, let's answer the question. What's the probability that exactly 4 toys are defective? What's the probability that exactly 4 toys are defective? X represents number of defective toys. So what we are looking for is probability that x equal to 4. What we are looking for is probability that x equal to 4. So for probability x equal to 4, that's f of 4. We plug in 4 into the probability function. That's 3,000 choose 4. 0.002 to the power of 4. 0.998 to the power of 3,000 minus 4 is 2,996. Then we can use calculator for the answer. But here we can see that this calculation is very big. In the calculator, 3,000 choose 4. 0.998 to the power of 2,996. In the calculator, the calculation is very big. The long time may be too long in the calculator. It's doable, but the long time may be too long. Here I use my calculator. I get 0.1338. 525,132. It's doable, but the long time may be too long. Especially 3,000 choose 4. 0.998 to the power of 2,996. The long time may be too long. Another way to solve this problem is we can try to use Poisson approximation. If we use Poisson distribution to approximate binomial distribution, the long time will be shorter. If we use Poisson distribution to approximate binomial distribution, the long time will be, in general, will be shorter. Note: in a binomial distribution, if n is large, and p is small, if n is large and p is small, and n times p is less than 10, then we can use the Poisson distribution to approximate the binomial distribution. With lambda equal to np, lambda equal to n times p. In the previous example, you can see that n is very large, p is very small. N times p, 0.002 times 3000 is 6. 6 is less than 10. N times p is 6. Here n is large, p is small. N times p is less than 10. So we can use Poisson distribution to approximate this binomial distribution. Next example. In example 4, use Poisson distribution to approximate the answer. Use Poisson distribution to approximate the binomial distribution. So same thing. Set out the problem exactly the same way. The X represents the number of defective toys in the box. The X represents the number of defective toys in the box. Then we use Poisson to approximate binomial. When we use Poisson distribution to approximate binomial distribution, lambda is always n times p. In the previous problem, n is 3000, p is 0.02. I have 3000 times 0.002, which is 6. That's lambda. So x here has a Poisson distribution, approximate Poisson distribution, with lambda equal to 6. Then the probability function. For Poisson distribution, the probability function is lambda to the power of x, e raised to negative lambda over x factorial. If we plug in lambda, we get 6 to the power of x, e raised to the power of negative 6 over x factorial. What we are looking for in the previous problem is what's the probability that exactly 4 toys are defective? What's the probability that exactly 4 toys are defective? We are looking for f of 4. We are looking for probability that s equal to 4. We are looking for probability that s equal to 4. Here, the support, I forget support. For Poisson distribution, support is from 0 to infinity. Integers from 0 to infinity. We are looking for probability that s equal to 4. Since x represents number of defective toys in the box, we are looking for a probability. We are looking for a probability that exactly 4 toys are defective. So we are looking for a probability that s equal to 4. If we plug in 4 here, we have 6 to the power of 4 e raised to the power of -6 over 4 factorial. Here we can see that if we use Poisson distribution, the computation looks much better than this expression. This is binomial. The computation here looks terrible. If we use Poisson distribution, the calculation looks much better. If we use Poisson distribution, the calculation looks much better, especially when lambda is small. Calculation looks much better. Then here I use my calculator. I get 0.1338 526 175. We can see that this is an approximate answer. Poisson distribution is an approximate answer, and this answer is very, very close to the actual answer. The only difference here, the first 6 digits stays the same. The only difference starts from the 7th digit. The first 6 digits stays the same. That means that's a very, very good approximation, especially when n is large, p is small.